Hello fellow problem solvers! So today we're going to be doing a problem from this Komal magazine from January 2002, problem A281. This is a combinatorics problem which is great if you're like in an intermediate level or getting to an intermediate level. You want to practice some of your skills like thinking, combinatorics, creative skills. This is a great problem for that. And I would invite you to try it out for a minimum of 30, ideally 90, not more than 180 minutes. If you'd like to go along with us, give this a go for the next 20 minutes. And now let's begin. So, with points in a plane, okay, no spherical linear, and we need to prove that we can color these points into colors red and blue, such that every half plane, which really means that once we draw any line that divides the plane into two, that if there are 3 points, at least 3 points on one side of that plane, then those points will have both red and blue, both a red point and a blue point. Okay, so how do we do this? Like, what are sort of your first ideas that come to mind? Well, for me, the first thing is like, what are my edges, right, of this plane? For example, this is a line I can draw. It's an edge line that might only contain these 3 points. And among these 3, I must have a red and a blue one. And then if I draw another edge line, just a line that's just over these 2, that's another edge line. I mean, if I had another point, say here, inside, I would draw this line instead. And I would have these edge lines. But it's telling me that on the edges of this configuration, I need to have both red and blue points. And now here's a point where I would invite you to pause for the next 15 minutes and try to see what would you do given this idea. Okay? And now here's the next bit. So if I'm concerned about points at the edges, and I need to be concerned about them, I want to focus on those. So because I'll be focusing on points at the edges, what should I do? And for me, the answer is, well, I should have a convex hull, which is a set of points that such like of these ends, say this is another configuration of these endpoints. It's a set of points such that once I connect them by line segments and I create a convex, what's this called? A convex n-gon, such that inside of which are all the points. Inside because no 3 are collinear. And now it makes sense for me at least, because I care about what happens when I move them by 1. What happens when I just like move the line here. It makes sense, for me at least, to alternate the colors on the convex hull. Say to make this one red, though that's not a great color, red. So let me do this red, 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 and color the other ones blue, blue. And now, what would you do? I invite you to pause for 5 minutes and try to push this problem further. And here's the next step. So if we have an even number of points here on the convex hull, we're pretty much done. The reason why is because no matter what line you draw, if it contains 3 points in the half plane, it will contain at least 2 points from the convex hull. Or actually, no, that's not necessarily the case. Now that I think about it, I could have points here, say 2 points here, and I could draw this line. So I can't have a guarantee that there are 2 points on the convex hull, but I can pretty much guarantee there's going to be at least 1 point on the convex hull. And now with this idea, I need to see, okay, if I have 2 points, if I have an even number of points in the convex hull, I'm pretty much done, right? Now the question is, what happens if I have an odd number of points in a convex hull, and what happens if I have this situation where I'm having a point on the convex hull and 2 points that are inside? Like how will I color these points inside the n-gon given this? And here's where I invite you to pause for the next 10 minutes and try to push the problem further. And now let me clear up this board, and here's the next step. Okay, so now we saw that this initial idea of just alternating the points here had some issues, right? We couldn't really finish up with that. We had problems with evens and odds, and what happens if there are 2 points inside of the convex hull, but that you can draw a line connecting these 2 points such that only 1 point is on the convex hull. And then we might need to figure out how to color these points appropriately. Now, the even and odd number of points on the convex hull also kind of makes our sort of coloring process a bit more difficult, because we're now concerned about like that extra case that could potentially hurt us, but potentially we could deal with that. Now, one way we could go about doing this is, like, say we have an even number of points, and then we're alternating red and blue, red and blue, red and blue. So red, red, red. Okay, here I made an odd number of points. I'll actually say, okay, we have a blue, a blue, a blue, and this one we'll color later. And now we could also create a convex hull inside our convex hull, right? Of the remaining points, we could connect them together to form a new convex hull. And it's going to be this. Actually, it's not going to be that point. It's going to be this point right here, this one, and this one. Now, supposedly, if we're going to draw any line that's going to divide the plane into 2, and if we're going to have, at least 1 point from this convex hull, at least 1, and at least 1 on this one, we could potentially have a case where we have 1 from here, 1 from here, and then maybe we can draw another convex hull to deal with the case if we have another point that's like here. And now there might there be a segment that looks like this? So there's another point in here, and then we can draw a triple convex hull and determine a coloring for them. And if we tried again to alternate, to do blue, red, blue, red, blue, red, who is to say that we won't have a blue, blue, blue situation? Actually, here's a red, red, red situation by the way we've alternated. So given this approach has sort of led us to a little bit of a complication. We have evens and odds. Now's the time to take a step back and see, okay, if this doesn't, let me see if there's another way I can color this. Maybe I don't need to color them all alternatively. Maybe there's another way to go about this. And one way is to say, okay, wait a second, let me try to do something simpler as well. Let me do this coloring as a process. Let me start off by calling all the points on the convex hull red. And now I'll be sure that every time there's a line, I'll have 1 red point, right? I'm good with that. Now, the problem is I might not have a blue point. So let me first color, because the reds are already satisfied. The reds are actually way too strong at this point. They are definitely satisfied. And let me color everything else, which I don't need to color red. So every other point inside, let me color blue. And now the trouble is, the reds are perfectly fine. Like I have them. I have more than enough reds. Like on on many lines, I'll have a situation where I didn't have these 2 points. Say these 2 points weren't here. Then if I drew a line like this, I would have 3 red points. I would have more than enough points on the convex hull to satisfy the conditions of the problem. Now my question for you is, can we change anything? Can we take any red points? And which kinds of red points should we switch to blue, such that we switch the minimum number of points we need to switch, and so that the reds remain the same, so the reds keep having this problem condition holds true, that once we take a half plane, they'll still be good. You'll have a red point in the half plane with at least 3 points, but that the blues also satisfy. But take the minimum amount. And here's where I invite you to work on your creativity, like ideas, and try to work on this for the next 5 to 10, maybe even 15 minutes. And now here's the big idea. So the thing is, if among like any 3 consecutive points on the convex hull, which are red, if there is a blue point inside the triangle formed by these red points, if there's a blue point inside, we're good. But, assuming say these 2 points don't exist, but if we have a triangle with these points which are red on the convex hull, such that there isn't a blue point among them, then we have a problem, right? That's where a problem lies. So, what is a way we could change this? And the answer is, well, we could color the one in the middle blue. And then we can continue looking at these triangles with all red, with 3 consecutive red vertices on the convex hull. Like 3 vertices which are consecutive and on the convex hull. And if there isn't a point that's blue inside that triangle, we color the middle one blue. Okay? That's the idea. Now, what happens then? First and foremost, we will not be able to do this process indefinitely, right? Because there are, like, how many triplets? If there are n points on the convex hull, there are n minus, there are n triplets. And this process needs to terminate. We can at most change a red point to a blue point, actually not even n times, but even less than that, right? N over 2, n over 3, or n over 2 times, something like that. We can't change it super often. Actually, no, it's n over 2 times at most. And with that, this process will terminate. And now does the problem condition hold true? And the answer is, well, let's see. If we're drawing a line that has a point, whatever line we draw that divides the half, we actually need to only look at the lines which have 3 points on one of the sides, right? Because any other line contains more. So those are the only lines we need to look at. Now, if a line contains 3 points, it's going to contain at least 1 on the convex hull. Maybe 2, we don't know. But it's going to be at least 1. If it's 2 on the convex hull, it's a red and a blue one. It's actually, let's actually double check this. Is it a red and a blue one? So if it contains 2 points, it's definitely going to contain a red one, right? Now, if the third point is not on the convex hull, then it's inside, so it's blue, and we're good. On the other hand, if it contains 3 points on the convex hull, and they are all red, by the virtue of our algorithm, it should also contain a point inside that's blue. Otherwise, we would have colored the middle one blue. And this, I think, sort of almost finishes up our problem, because now we say, okay, there's 2 cases. Whatever line we draw, it's either a line which has 0 points that are... Actually, we can look at it like this. We can look at these triangles and say whether the line that we're drawing... Now I'm thinking of a good way for us to actually write this down. And I think the best way is to say there's 2 possibilities. Either the line that we're drawing contains internal points or it doesn't. If it contains points on the inside, they could all be blue. So let's actually look at a better way to do this. if it contains 1 point on the convex hull and 2 points inside which are blue, then this point on the convex hull is red. Why? The answer is we didn't color it blue. Why? Because the 2 points, if this one was colored blue, if and only if in this triangle formed by these consecutive 3 points, we didn't have a blue point inside of it, but given these 2 points are in the convex hull, given these 2 points are on this line that divides the plane into 3 here points, given that, we know this one is red. And if we had 2 points on from the convex hull, then we know, okay, one of 2 things. If we have 2 points and one from the inside, if we have 2 points, one of them is red, at least one of them is red, because this thing won't apply to triangles which have all vertices which are red. So among any 2 consecutive vertices, we'll have one that's red. So that gives us the red point and the blue point, and we have a blue point if there's a point from the inside. On the other hand, if we have 3 points that are on the convex hull, that are on the side of the line, then either there's something in its entirety in the triangle formed by these 3 points that's blue, and if there isn't, the middle point is colored blue, and so we're done. And that's pretty much it. Not the middle point, but at least one of the points by our algorithm is going to be colored blue. So say this one was colored blue, say this one wasn't. So this one will never be colored blue because of, let's say, these 2 points that exist, then this one was, say, colored blue because of, let's say, this triangle. And if we drew one line here, then this point over here would be red, red, and blue, and that would be good. We'd have a point that's red and a point that's blue on both sides of the half plane. And this finishes up the problem. Now, I really, really like this problem because it's just this. You start off with this idea of, let me just do the convex hull and alternate because I care about the convex hull here. Because that gives me like this minimum thing. Like if there's a line with 5 points that satisfies, then the line with 3 points also needs to satisfy. But if I have a line with 3 points that satisfies the condition, then if I draw a line with 5 points, it will by definition satisfy. So that's the first thinking, why I like the problem. You have a little bit of that, sort of a point or two, like your first sort of thing you see in the problem, first idea. And then you see, okay, let me do this convex hull. Let me alternate the points. You see that doesn't work. You see that will give you a bunch of complications. And then you need to draw yourself out of it and try to see, okay, let me do it different. Let me color all these points red. And then depending on whether I need to change the color of a point, let me only change it to blue on the convex hull if I need to do it. And then you see, okay, if I take this idea, I'll only change a point to blue if I need to do it. If you take this idea and transform it into an algorithm, you get this, and then the problem gets finished. And so that's why I think this was a very cool problem for us to solve. This finishes up our problem, and as always, thanks for problem solving.